السلام عليكم. النهاردة 25/11، اليوم 19. لسه عندي تاسكات في السي وشوية في بايثون، فيلا بينا. خلينا نرفع الفيديو الجديد. خليني افكرك برضو كالعادة، لو في صلاة متأخرة عليك صلي وتعالى. شوية شاي، مية، حاجة تاكلها. يلا بينا. خليني اعدل حاجة كده. محتاجين نقلل البرايتنس. اوكي كده حلو. يلا بينا. النهاردة رابع يوم في السي، مش رابع يوم في حياتي يعني، بس رابع يوم اذاكر فيه سي، احل في هذا التايم فريم من السلسلة الغريبة اللي انا عاملها. That's it. Next. Publish. ايه الغماء ده؟
här is your småpet
in memory yet. We'll see how that trick gets played later on. But for now, the important part to remember is that when things are stored in a ELF file, they're all contiguous in that disk space. There's byte after byte after byte of useful information. When it gets loaded into memory, specific chunks are loaded in specific places. Each other, they're not necessarily going to be contiguous. Some of them are going to be, hundreds of thousands or trillions of bytes away from each other. But that doesn't mean we're using all those bytes. We're only going to be using the chunks that we have actually in use, for lack of a better term. So when we're loading these in, that first thing that the loader is going to do is figure out which segments of the ELF file need to be loaded into which addresses in the running process's memory space, in the memory image. I'm going to use lots of different terms to refer to roughly the same thing. I might talk about the memory space, I might talk about the memory image. What I'm talking about is, again, this thing from the previous slide, where we have this drawing here, where we've got our stack that grows towards lower addresses. Our memory map region growing towards higher addresses, our heap growing towards higher addresses. Things along those lines. So, so rather than just looking at this on a slide, let's look at it in the real world. In Visual Studio Code. So we can just looking at this on a slide, let's look at it in the real world in Visual Studio Code. So what we have on the screen here is just a bonkers simple hello world program, and it has two calls to printf because we're going to be showing off how the dynamic linker works a little bit later on in this lecture. Right now, we're just talking about loading the executable. So if I do a readelf of LW, this is going to show, so if I do a readelf of LW, this is going to show me all of the headers that instruct the loader for where to put what bytes from the file that instruct the loader show me all of the headers that instruct the loader for where to put what bytes from the file into what bytes in the entire address space of the program. I'm getting a little ahead of myself. If we really want to start from the absolute beginning, we can run, we really want to start from the absolute beginning, we can run readelf-h, which gives us the headers of the entire thing. This is starting from the very beginning of that ELF file, right? Anything that reads a file is almost always going to read it from the very beginning to figure out what format it's in, to figure out what's important. And the important thing we want to get from here is A, we have this magic chunk of bytes, which means that this is a ELF64 format file. And then we know eventually when we get started with the code in this running program, we're going to jump to the instruction stored at hex 400/400. And to eventually when we get started with the code in this running program, we're going to jump to the instruction stored at hex 400/400. And we have a bunch of program headers. We have 9 to be exact. The headers are each 56 bytes and they're going to be interpreted in a certain way. So if we come back to our headers, we see these 9 different program headers. So these are the 9 different locations that the loader is going to pick up out of this file. 9 different program headers. If we come back to our headers, we see these 9 different program headers. So So these are the 9 different locations that the loader is going to pick up out of this file. These 9 certain way. So if we come back to our headers, we see these 9 different program headers. So these are the 9 different locations that the loader is going to pick up out of this file and put down into memory at a given space. This first one is saying put the header in memory where you want to put it. The second one, this interp section, is special for dynamically linked libraries. We'll talk a little bit more about that a little bit later on. So these next 2 lines are probably the most important ones for us understanding how do we go from everything we're seeing in the PowerPoint to how do we go with an actual program that's actually running on our actual machine. This first chunk here is loaded in as readable and executable. It's loaded in at address 400,000, and it's loaded in from offset 0 within the file for hex 6F0 bytes. So what this tells the loader is start at the beginning of the ELF executable file, pick up 6F0 bytes, and shove them down into the memory address space of this newly about to be running process at address 400,000, hex 400,000. That's what that part needs to do. And it says it's going to make it readable, not writable, and executable. Well, you'll probably guess what this is going to end up being. The next part gets loaded in from offset E10 in the file for 220 hex 220 bytes, but it's actually going to load in 228 bytes into memory there. This is where maybe we'll figure some interesting things out here as well. So we're loading in more bytes than we would have otherwise needed to pull in. And we're going to start that load at memory address hex 600E10. These are all just numbers, right? But what's important is how they're all going to work together when we start using the program. So let's switch back over to our slides really quick. We see that in the ELF file, in that entire ELF format program, we have the program header table, which is what we're reading right now in VS Code. That tells us where each of these different segments exist and how to load them into memory. That's the information for the loader. The other set of information that's in here is the section header table. This section header table actually tells us which of those sections of that ELF file correspond to which chunks of the ELF file. This is basically saying ELF has a specific format, and there's lots of different types of sections that go into that format of an executable. What's really important here is that sections like .data and .bss and .text are relevant for linking and GCC and stuff like that, but they're not explicitly relevant for the process of loading that program in. The loader doesn't care whether something is in .text or in .ro data. It knows that it should be loading those things read-only at a specific offset. That entire chunk of memory in that entire segment is loaded in all as one chunk of stuff. So if we look at our section segment, mapping here back in VS Code, we see that 01 offset 2 is going to have all these different sections in it. So it's got the interp section, which is a set of instructions for how to start using a dynamic loader. And the important ones we have here are .text and .ro. Data. Those are ones we have here are .text and .ro data. Those are the read-only sections that we know we need to have in there to hold the instructions of our program, as well as any read-only constants that are global variables in our program. Likewise, offset 3 here includes the data and BSS sections. This BSS here is why, even though we are loading in hex 220 bytes from the program on disk, we're loading it in as hex 228 bytes in the running program. This is because the BSS section doesn't take up space in the file, but it still exists in there. And when it gets loaded in, it needs to have that space expanded out. And when it gets expanded out, it's getting fresh, clean bytes from the operating system. All those fresh, clean bytes are zeros, and it goes about, and it saved 8 whole bytes in this instance. So now that we've done that loading process, we're going to move on to how do we actually get started with this program as it starts running. So when we look So when we looked at that, how do we
إذا عدنا إليكم من جديد. ريحت و آخر مرة سجلت امتى؟ يعني نمت شوية كده وكلت والدنيا تمام، ويلا بينا نكمل ساعتين بالليل كده. ما لو عملت كده يبقى أحسن، صح؟ زي الفل، يلا بينا.
Actually get started with this program as it starts running. So when we do how do we actually get started with this program as it starts running? So when we looked at that, how do we actually gets started with this program as it starts running. So when we looked at the headers back over here in VS Code, we saw that one of those elements that's always going to be in an ELF header is the entry point address. This is the first address that gets jumped to when this program actually gets started. So if you ever wondered what's the very first assembly instruction of our code, it's the thing pointed to by that variable stored in the header of the ELF file. I'm going to show you really quickly in the slides what it is we're doing. Then we're going to move on to actually looking at it in VS Code in that Hello World program that we have in our open window. So almost always that first hex, in this case hex 400, is going to be the very first instruction of an underscore start program, which is just a handwritten executable program that will load a compiled version of the libc start main function. And it just does some super basic housekeeping. Then it goes ahead and loads the compiled version of that. A compiled version of the libc start executable program that will load a compiled version of a handwritten executable instruction of an underscore start program, which is just a handwritten to be the very first instruction of an underscore start program, case hex for open window. So almost always that first hex, in this case hex 400, is going to be the very first instruction of an underscore start program, which is just a handwritten executable program that will load a compiled version of the libc start main function. And it just does some super basic housekeeping. Then it goes ahead and loads the compiled version of that libc start main. What libc start? It goes ahead and loads the compiled version of that libc start main. In addition, so what libc start main is going to do, it's going to call the init function. Libc start main is going to do, it's going to call the init function. There's also a .fini for like finishing up. So this basically allows you to load specific things that need to load before absolutely everything else in your program. And then there's going to be a fini section for running code at the absolute end of your program. And this kind of doesn't make too much sense. It's like, why would I want to load code that wasn't compiled into my program specifically? Well, one really important, useful thing that you can do with all of your code that you ever run is profile it. You can say, well, I wrote this program and it is compiled, and I want to not just run it, but I want to measure exactly how long different functions take, exactly how many different functions get called. I basically want to instrument that to figure out how my program is running, which parts are fast, which parts are slow, which parts are common, which parts are rarely or never called. And I can't do that successfully without profiling the code. So one thing that you can do in that init section is initialize the profiler and just jump to the profiler and do what it needs to do. After that has been done, the libc start main will finally call main. Main will return. Libc start main will return. Main. Main will return. Libc start main will return. And that underscore start function will halt. It'll stop the entire process. So a few other specific things that libc start main will do is it's going to set up argc and argv on the stack. It's going to set up the environment variables. And then it's going to call main. It's going to take that return value of main and it's going to send it back to the shell or whatever the parent process was that called this process, that created this new program, usually the shell. So because I have a configuration file that will launch GDB and point it at the right header files to allow us to do a little bit of extra fancy debugging, once I open this dev container up and let it build the dev container, and follow the instructions in homework, I think it's lecture5.md, I can hit my F5 button to start the debug task. And the debug task also stops at the first instruction of main. It has an option stop at entry. And the very first thing here is printf hello world. So this debugger session has stopped before I ran printf hello world. So if I continue it, it's going to print to the screen twice with no new line because I forgot to add them, then it's going to quit. So super basic, that's a GDB execution, not that big a deal. If we want to see how start works, I can go into the debugger and I can create a new breakpoint. And this new breakpoint is going to be on the underscore start function. So whenever my program finds an underscore start function, it is going to pause. It's going to break. So let's start over. So we broke on that start. We are sitting there, but there's an unknown source, right? There's no way for you to actually see what that is. But recall from a few slides ago that real underscore start is handwritten assembly. It's just a very small amount of code that is explicitly specific for x86, 64. Linux variants. What I would prefer here is I want to write as much C as possible that's going to be cross-platform, and I'm only going to write assembly when I absolutely need to. So this underscore start is a very, very basic .o file that was handwritten assembly code that's specific to x86 64. We'll see it in just a moment. But the basic idea here is you have no idea what's going on, and the important thing, and I have it in the notes, is to do a step into, and this is going to step into libc start main. So now that I've jumped past the assembly only code in underscore start, I'm in the C code of libc start main, that function that is actually doing the real work of the underscore start function that sets everything up. So what this is going to do is it's going to take as its arguments things like the location of main, the location of init, the argc, which is the count of arguments, and the argv, that vector of string constants that are all the arguments passed into that function, and it's going to do what it needs to do to get everything set up. It's going to set up the environment, it's going to start the dynamic linker, it's going to do all of these different things, and then it's going to jump into main. So you, if you want to, you can step through this function and see it do the DLL linking, you can see it try to call init, you can see it try to set up the add exit handlers. So add exit is this thing where you can say, before my program ends, however it ends, whenever somebody calls exit to just kill the program, run this thing first. And maybe that's going to do some debugging output, maybe that's going to do some cleanup, whatever have you. You can call add exit to basically install a function that gets called before your program ends. And so that's one thing that this is setting up. And you can just keep on going through. So it says, oh, if init is there, then call init. There is an init that I think we can, yeah, we don't jump into it in this case. Keep moving through these calls, and eventually we will get to that call to main. And I totally stepped past it, and now we exit, and we're done. So if you want to take a closer look at how libc start with instruction in main, that's a computer science parlor trick if I've ever heard one. So let's go back to instruction in main. That's a computer science parlor trick if I've ever heard one. So let's go back. Back to dynamic linking, right? That's the other big part that this is about. So in that run of the underscore start function, we were hitting the dynamic linker and it was doing a few things at the very beginning of the running program, but we didn't really go into too much detail of what's going on. There's a lot that goes on there of exactly how all this works, but we're gonna hit on a few important topics right there that are mainly the ones covered in the book. So what we've looked at so far is static linking, where we take every single library function that we've ever needed and we put it all into one happy executable, and then we've got our data section, we've got our text section, and more or less that's all you need. You've got your variables, you've got your heap, you've got your stack, and you've got your text. You're done. You're good to go. That that's not the best way to do things. It's probably going to be better if we keep our libraries that are really, really common to all of these programs separate from the actual unique code that we wrote to make our programs do what we want our programs to do. So we do this using shared libraries. Shared libraries are libraries like we saw before that have things like printf or puts or cosine or sine or whatever have you, and we put them into this special format that allows us to link them either at build time or at load time. So there's some pluses and minuses to these things. Most of what we're going to go over is the pluses that come from this additional complexity of using the dynamic linker, but there are a few pluses to the static side. So with a statically linked executable, no matter which Linux machine you're on, if you have compiled something for 64-bit Linux and it's not using any special features of the kernel, it's just going to work. It's not relying on anything but itself to get loaded and get run. And that's actually really, really powerful. You don't have to worry about, oh, do I have the right library installed? Do I have the right version of the library installed? Blah, blah, blah. But in most cases, that benefit is not going to get outweighed by all of the downsides to using static linkers. So if we go over here to our executable, so if we pull up our shell and we look at benefit is not going to get, not relying on anything but itself to get loaded, no matter which Linux machine dynamic linker, but there are a few pluses to the static side. So with a statically linked executable, no matter which Linux machine you're on, if you have compiled something for 64-bit Linux and it's not using any special features of the kernel, it's just going to work. It's not relying on anything but itself to get loaded and get run. And that's actually really, really powerful. You don't have to worry about, oh, do I have the right library installed? Do I have the right version of the library installed? Blah, blah, blah. But in most cases, that benefit is not going to get outweighed by all of the downsides to using static linkers. So if we go over here to our executable, so if we pull up our shell, and we look at the file, this hello world.out, it's 11 kilobytes, and this is our dynamically linked version. If instead we were to say, hey, GCC, how about you compile everything you need into that program? It's just printf. How bad could it be? Well, we can do exactly that. We can run this code, and any guesses as to how big that's going to be? I'll show you right now. Same line, 828 kilobytes. So the better part of a megabyte is needed for us to kilobytes. So the better part of a megabyte is needed for us to run Hello World twice. That's only slightly ridiculous, but that's the entirety of the C standard library brought along for the ride in this program. So as I mentioned in the previous video, this is ridiculously inefficient. Not only am I putting that 800 some kilobytes in my hello world.out, I'm putting it in bash and LDD and this and that. And every single thing I compile with the standard library of GCC, I get an extra almost megabyte of storage used on my hard drive. And there's lots of executables on your hard drive. And even worse than that, there's a lot that you load into memory. If you can't share that memory among different places, you're very, very quickly going to run out if you're running lots of different programs that use the same library. It's the same stuff, but it got linked into different statically linked executables in different places. So it would be a lot better if we had one copy that we could keep someplace in memory and then just refer to it from other places. Not only will this save us disk space, it'll save us memory space. And when we save memory space, remember that makes our program faster. The less memory that gets taken up with this copy of the C standard library or that copy of the C standard library, the more of the meaningful stuff can stay in L1 or L2 cache and go super, super fast. So where do we space? Remember that makes our program faster. The less memory that gets taken up with this copy of the C standard library or that copy of the C standard library, the more of the meaningful stuff can stay in L1 or L2 cache and go super, super fast. So where do we put all this stuff in memory? This is one of those big challenges. We are trading a moderate amount of complexity for a lot of performance in specific situations, but we've got to figure out how to do it correctly. Remember, this is our most important thing. If we don't make it correct, we don't have a job. So we need to make this work properly, even though there's only one copy. And there's going to be a few challenges that come to mind. This is going to be another really great example of what the challenges are that we see as system designers. We see that there is a problem. We're using way too much memory. And when we use too much memory, our programs are slow, we run out of disk space, we run out of memory, we can't run as many programs at the same time. There's lots of reasons we want to use much less memory. And we saw, hey, there's this opportunity. We're taking the same thing and we're copying it over and over and over again into different places in memory. And in theory, we don't need to have all those. And that's our challenge. That was the insight that somebody said when they invented dynamic linking. They said there's gotta be a better way. We can't keep doing this stupid thing of loading the same thing in different places. But it's not just like, oh, just load it in the same place, boom, done, right? It's a lot harder than that. And we're just gonna see the final answer. But what we wanna try and develop in this class is our ability to see a problem like that and say, aha, here are a few of our rules of thumb for building a system, designing a system, whatever have you. Here's how we're gonna approach a new problem that we've never seen before. So we're just gonna cover the story of how does dynamic linking work, and hopefully you'll be able to approach problems you've never seen before and use the same approach. So how do we make it correct? How do we make it fast? So our first problem with how to make it correct is that in a statically linked executable, all of our text is in this text section. All of our global variables are in this data and BSS section. That's everything that's coming out of that executable file on disk and getting shoved into the segment of virtual memory. Disk and getting shoved into the segment of virtual memory as gets loaded in the program image. When we're loading things into this memory mapped region, we're doing pretty good. We've got a place in memory where it's like, this is where our shared libraries will go. But different programs are going to load them in different places, and maybe even the same program is going to load them in different places at different times. So our first challenge here is that everything in this text section has to refer to not only its own global variables, but possibly global variables it uses from other libraries, or global variables getting used from the main executable correctly. And it doesn't know where it's going to be. So we can't use any absolute addresses in that process of time. talking about anything, whether absolute address, and it doesn't know where it's going to be. So we can't use any absolute addresses in that process of talking about anything, whether it's in our data section of our own individual library or it's a global variable that was an extern. So maybe libvector.so relies on the C standard library in order to get its job done, and maybe it calls things in its text. Maybe it uses the global variables from libc.so. That's legal. It's a symbol, it gets resolved, but the problem here is that those symbols aren't necessarily going to live in the same place at the same time. But this text is going to be set in stone as soon as you compile that. As soon as you gcc-c on libvector.c, you've got an executable. That thing needs to work, whether it's loaded into my program or your program or somebody else's program, and it might get loaded into different places.
Hi.
It might get loaded into different places. The solution to this
Vamos.
is relatively straightforward, and we've already seen a few hints about how this works. What we're going to build here is what's called position independent code. We are going to create segments of code such that no matter where they are in the address layout of a running program, they will always function correctly. Valid or your program or somebody else's global variables, but possibly global variables it uses from other libraries or global variables getting used from the main executable. correctly. And it doesn't know where it's going to be. So we can't use any absolute addresses in that process of talking about anything, whether it's in our data section of our own individual library or it's a global variable that was an extern. So maybe libvector.so relies on the C standard library in order to get its job done, and maybe it calls things in its text, maybe it uses the global variables from libc.so. That's legal. It's a symbol, it gets resolved, but the problem here is that those symbols aren't necessarily going to live in the same place at the same time. But this text is going to be set in stone as soon as you compile that. As soon as you gcc-c on libvector.c, you've got an executable. That thing on libvector.c, you've got an executable. That thing needs to work, whether it's loaded into my program or your program or somebody else's program. And it might get loaded into different places. We're going to build straightforward. The solution to this is relatively straightforward, and we've already seen, a few hints about how this works. What we're going to build here is what's called position independent code. We are going to create segments of code such that no matter where they are in the address layout of a running program, they will always function correctly. Address of code such that no matter where they are in the address layout of a running program, they will
Only 3 times have we ever hit 107 in Salt Lake City. I went up to like here on this trip to show. Okay. I think, yeah.
will always function correctly. So we don't know what address offset it's going to be at, but this thing that gets loaded into memory, if we go back over here, so libc.so can't be sure about where it gets loaded in memory. It can't be sure about what program is loading it, but what it can be sure of is what it can control, right? So this thing that gets loaded into memory, if we go back over here, so libc.so can't be sure about where it gets loaded in memory. It can't be sure about what program is loading it. But what it can be sure of is what it can control, right? What it can control is its own layout, its own text, and its own data. So what it's going to do is it's going to say, whenever I refer to something in my own data section or in in my own text section, I am going to refer to it using PC relative addressing. Because if I know where I am in the text, I know how far away a specific variable is in my own data, I know how far away any of those things are, and I'm going to use my own data section and my own text section to talk about things in this relative manner so that I can be positioned anywhere that I want within the memory layout of that running program. So if we know all these distances between things, we can always use PC relative addressing. So by compiling our libraries with position independent code, we will be able to make sure that all of their references internally will be consistent. They will all work regardless of whether they are loaded in any given address. This is going to be the solution for local references. So anything static. Static is always going to be fixed purely by adding position independent code. But unfortunately, we're not out of the woods yet. We also have to talk about those references that go across the boundaries between different libraries. Remember that it's legal for you to have an extern that comes from another library or have an extern that comes from the main program out into a shared library. So let's talk about how we get all this stuff to work. So remember that our linker is going to do these two different things. It's going to resolve the symbol, it's going to figure out which one it needs to use, and then it's going to relocate based on that. Normally, what we've been talking about so far is that we've been relocating during build time when we know that we're creating something that's all special, just built for just us. But in the dynamic library world, we need to split this process up into two segments. One, we've got to find those functions and find their signatures so that we know how they're going to be called, what library they're going to be called from, and load those relocation entries in, saying here is where a function with this many arguments of this kind is eventually going to be put. And we're going to add a interp section that will start this entire process of eventually linking up the procedures and the global variables that are part of that dynamically linked library. So then when we load the entire program, the dynamic linker is going to relocate the text and data based on wherever it's supposed to end up, based on how that dynamically linked executable was created. And then it's going to relocate the references to any symbols that are shared in that library. So here's an overview of how the whole entire thing is working when we're doing dynamic linking. What's really important here is that there's things happening at build time and there are things that are happening at load time. So at build time, we need the relocation and the symbol table information. We need to know that these symbols exist here. We need to know how big the symbols are. We need to know that they will eventually be included. So we can't do the linking process at build time without access to the libraries. But the important thing is that while we do need the symbol table information and the relocation entry,